Hello guys, welcome to my channel. My name is Jesse. Today we will be talking about natural number. So to talk about natural number, we need to talk about what is natural number. So a natural number, intuitively, we know that a natural number is will be started. We'll be starting from 0, 1, 2, 3, and so on. This is what the intuition of us thinking about natural numbers. However, by solely intuitions, it is not enough to define the natural number. To define anything about the mathematics, we need to have a very logical and formal way to define the mathematical model, including how we define natural number. So to define natural number, we need to use something called axioms. So an axiom is a statement that is taken to be correct, to be true. And the axioms is to serve as a premises or starting point for the further reasoning and also argument. For example, proof. Proof is a type of reasoning and argument. So to talk about a natural number, axiom of natural number, we need to talk about the statement. So the first statement of natural number, of axiom of natural number is 0 is natural number. So this statement includes one element into natural number. This is a very good starting point to actually define the entire system of natural number. So our second statement is very crucial because it defines most of the natural number system. So it states that if n is a natural number, this statement will imply that n plus plus is also a natural number. So these two axioms combined, you will form a series of a number. So what is n plus plus? N plus plus is what we know as a successor. So n plus plus is the successor of n. Okay, so you just think of it as another natural number that in the form of this. So according to axiom number 1, 0 is a natural number. According to the axiom number 2, if n is a natural number, then n plus plus must be a natural number. So combining 1 and 2, we will have 0 plus plus is a natural number. So because 0 is a natural number, it automatically implies that 0 plus plus will be the natural number according to second statement of axiom of natural number. So 0 plus plus is a natural number. By using the similar step, we can conclude that 0 plus plus is also a natural number. And we can keep moving on until you have infinite number of elements for a natural number. And then the crucial part is that we define 0 plus plus as 1 and 0 plus 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 as 2 and 3, 4, 5, and so on. So this is how we begin to define our natural number system. So are we done by using these two axioms? Actually, we are not done yet because these two axioms is not enough to define what is natural number. Because these two axioms doesn't prevent this kind of things happen. 4 equals to 0. So 4 equals to 0 is a true statement according to first two axioms. Therefore, we need to prevent it. So to prevent it, we need another axioms. The third axioms is state that suppose you have suppose n is natural number. Then for all natural number n, we have n plus plus would not be equals to 0. So what does it mean by for all n plus plus would not be equals to 0? This means that any successor of a natural number will not be equals to 0. It is impossible to be equals to 0. This is what the axiom 3 talking about. So how do we prove that 4 is not equals to 0? So to prove this statement, we need to assume the opposite. So assuming 4 equals to 0, this will imply that 3 plus plus equals to 0. And then we know that from the third axioms, any successor of a natural number is not equal to 0, but the successor of a 3 is equal to 0. This contradicts with the third statement of the axioms of natural number. Therefore, a contradiction happened. The contradiction happened is due to the fact that we're assuming the opposite. Therefore, 4 must not equal to 0. So this is how we prove 4 is not equal to 0. So with these three axioms, is it enough to define what is natural number? Is it enough to complete our system of natural number? No, it is not enough because it doesn't prevent 4 to be equal to 3. So using this statement is true by these first three statements. Therefore, we need another axiom to prevent this kind of things happen. So the fourth axiom states that for all natural number n and m, if n plus plus equals to m plus plus, this will imply that n equals to n. And so this statement states that any successor of a number, if that number successor of a number equals to another successor of a number, then those two numbers must be the same. It must not be another case which is different. So this is what axiom 4 trying to tell us. So axiom 4 prevent 4 equals to 3. Here's how. So suppose you wanted to prove 4 is not equal to 3, then by assuming 4 equals to 3, we will arrive to the conclusion that 3 plus plus equals to 2 plus plus, and then according to 4 axioms of natural number, we know that this implies n equals to m. This implies 3 equals to 2, according to fourth axioms. And then we can keep using the fourth axioms as the procedure. We will eventually arrive to 2 equals to 1 and 1 equals to 0. So we know that 1 equals to 0 implies that 0 plus plus equals to 0. And this statement contradicts with the third statement, which state that any successor of a natural number is not 0 here. You see? Contradict with the third statement. Therefore, it must be 4 is not equal to 3. So this is, sorry. So this is how you construct the fourth axioms. So yeah, is it enough to use just 4 axioms? No, we have a last thing that needed to be solved. The last thing is the mathematical inductions of a natural number. So mathematical inductions of a natural number is actually not provable. It is actually an axiom. You always use that to prove the theorem that includes the natural number system. And you always use that without proof. Actually, that is an axiom of natural number. So the fifth statement states that suppose suppose Pn is a statement, and then if this statement meet the following conditions, where P0 is true. Okay, this is the first conditions that is needed to be met. And the second condition is if Pn is true, this will imply that Pn++ is also true. Then with these two conditions, the whole statement will imply that for all n, Pn is true. So this is the scheme of the mathematical inductions. And this must be an axiom in order for us to further prove the theorem that includes the natural number as the system. So that's all for my video. Thank you guys for watching. See you in the next video. Thank you.